All right. This is CS50. This is the end of week 3. And if you haven't taken advantage already, know that there will be lunch this Friday as usual, where you can enjoy a good conversation and food at Fire and Ice with some of CS50's staff and classmates. Head to this URL here. Now, you may recall, or you may soon be acquainted with, these things here, which are given out at the end of a semester for many classes, so-called exam blue books, in which you write your answers to exams. Now, I have here 26 such blue books. On each of them is written a name, A through Z, and indeed the names are that simple, A through Z. And one of the goals at hand today is going to be to continue what we started on Monday, which is not so much looking at code, but really looking at ideas and problem solving. Right? One of the goals and promises of this course is to teach you to think more carefully, more methodically, and to solve problems more efficiently. And indeed, we can do that really without even touching a line of code. So I have a couple of elephants up here today, orange and blue. If we could get one volunteer, maybe from farther back than usual. How about right there? Come on down. The goal of which is going to be to help us administer this exam here. What's your name?
Mary Beth.
Mary Beth, come on up. Let me get the microphone here for you. All right, nice to meet you.
Nice to meet you too.
All right, so I have here blue books A through Z, and I'm going to pretend that I have I'm one of the students, and they're coming in somewhat randomly at the end of a 3-hour exam block. So they're ending up in some semi-random order like this. And now your job in just a moment is going to be, this is actually how they get turned in at the end of the class, most likely. Your job now is going to be, quite simply, to sort these blue books for us from A through Z.
Oh, this is going to take forever.
And we will watch as you do this.
No
No pressure.
No pressure or anything.
Oh, and for fun, let's put up a timer.
Oh, yeah. So much fun. So much fun. Yes.
I can hold the mic for you.
Thank you.
All right, we've just doubled our speed. So in the meantime, let me pose what's going to be the question for Mary Beth is, what is she doing? How is she going about solving this? And in fact, you might not have ever thought about something so simple as when you pick up 26 books like this, which do have a natural ordering to them, what is the process that you actually use? Is it fairly random, just picking the first one you see and putting it in its place? Do you first move your hands around looking for A, then looking for B? Do you take a look at a pair of them side by side and just say, wait a minute, this isn't right, and then swap the order? We saw already on Monday that there's a number of ways in which we can do this. And indeed, as we near the end here, I would take note, perhaps, of what Mary Beth is doing. We have a few piles, it seems. A bigger one, 3 smaller ones.
I am basically ordering them when I find... I'm ordering them when I find 2 letters that I know are together in the sequence. I put them together so that I don't have to worry about keeping track of a whole row of books. It's just, oh, A is first. I've got this stack
So almost
here.
like puzzle pieces that have the right shape to match up with each other.
Pretty much, yeah.
Okay.
And then C, F, G.
Excellent. And now each of these piles is presumably sorted?
L, M, N. Yep.
All right.
O, P. And then
A through Z.
A. All done.
All right. Congratulations. You did it. All right, you have your choice. Blue. All right. Thank you for that. So Mary Beth did propose what her approach was, but what is another approach how you might go about sorting these things? What would you have done? All right. The record to beat would have been 1 minute and 50 or so seconds, plus the ones I forgot to count. What would you have done? Yeah.
Take the stack and start from the beginning.
Okay.
Check 2 papers, and if the top one is higher, then leave it as they are. If the bottom one is higher, then switch them.
Okay, so starting at the top and the bottom, and then working your way inward like that, swapping them. Okay, so similar, a little similar in spirit to bogosort, but choosing the extremes, not the adjacent pairs. But the short of it is that there's surely a bunch of different ways we could have do this. And frankly, I think you kind of adopted a couple of approaches, right? You made sort of 4 sorted piles, and then effectively merged them together. And that's, dare say, another technique altogether. You didn't treat it as one big pile. You divided the problem into 4 quads, if you will, and then somehow merged them them in the end. So let's consider ultimately how else we might do this. We formalized the notion of bubble sort last time, and bubble sort, recall, was an algorithm that we visualized with 8 of your classmates up here, seemingly randomly sorted at first, and we then decided pairwise, if 2 elements are out of order, simply swap them. So 4 and 2 are obviously out of order, so those 2 classmates switched positions. And then we repeated with 4 and 6, then 6 and 8, on each iteration moving to the right. So given 8 people, how many pairwise comparisons did I do while walking from left to right in one such iteration? How many comparisons? 7, right? Because if there's 8 people, but you have to pair them and you keep moving 1 hop to the right, you're not going to have 8 comparisons because you can't compare an element against itself or it would just be pointless. So you have 7. Or more generally, if we have n people, we do n minus 1 comparisons with bubble sort. So let's consider now how good or bad bubble sort actually was and try to give ourselves a vocabulary with which to critique algorithms like this and soon our own. So the first pass through bubble sort, the first time I walked from left to right across the stage, took me n minus 1 comparisons. And that's going to be my unit of measure, right? I was kind of talking and strolling somewhat fast, somewhat slow, so counting my number of seconds isn't particularly telling, but counting the number of operations that I did on Monday, comparing 2 people, that feels like a nice unit of measure. So n minus 1 steps the first time, but then what happened after that? What's the one upside of one pass through an otherwise unsorted list? What can you tell me about the element who was all the way over there? Yeah. That was the biggest element, right? Number 8, even though she started here, every time I compared her against a neighbor, she kept bubbling up to the right-hand side of the list. And indeed, that's where the algorithm gets its name. Now, by that logic, how many comparisons need I make on the second time I make that pass from left to right? N minus 2, right? It would just be wasting my time if I keep comparing 8 against someone else because we already know she was in the right place. So that's a bit of an optimization. So the next pass is going to be plus n minus 2 steps, where again, n is the number of people. Now you can kind of extrapolate, even if you're not a computer scientist, how this ends. At the end of this algorithm, presumably, you've got just one comparison left. You have to kind of fix the beginning of the list in case 2 and 1 are out of order and should be 1 and 2. So this bottoms out at plus 1 final comparison. Now the ... kind of waves its hands at some of the juicier details, but let's just go ahead and simplify. If you recall from high school, frankly, a lot of you had math books that had a little cheat sheet on the front cover or the back cover that showed you what series summations like this ultimately added up to in the general case if you have a variable like n. And indeed this one, if you looked at your old school math book, you would see that this actually adds up to this sum here, n times n minus 1 all divided by 2. So for now, let me just stipulate this is true. So on a leap of faith, that's what this sums up to. And we could prove that in a more general case. But now let's expand this out. So let's multiply this out. So that's n squared minus n, all divided by 2. Well, that's really n squared divided by 2 minus n over 2. So that's all nice and interesting. But what happens if we now plug in a value? Suppose I didn't have 8 people, but say 1,000,000. And 1,000,000 just because it's a pretty big number. Let's plug that in and see what happens. So if I plug 1,000,000 into that formula, I'm going to get 1,000,000 squared divided by 2 minus 1,000,000 divided by 2. Now what's that going to equal? So 500 billion minus 500,000. And if I actually do that math out, that means that sorting 1,000,000 people with bubble sort might take me 499,999,500,000 steps or comparisons in the end. We're just extrapolating. Now that feels pretty slow, but frankly, measuring one particular input like this isn't all that telling, but indeed it does suggest that as n gets larger and larger, this algorithm kind of feels worse and worse, or you really start to feel the pain of that exponentiation, that n squared, which adds up pretty fast. And this detail isn't lost on people. In fact, some years ago, a certain senator who was campaigning sat down for an interview with Google's Eric Schmidt, CEO at the time, and was challenged with a question much like we're exploring today. Let's take a look.
Now, Senator, you're here at Google, and I like to think of the presidency as a job interview. Now, it's hard to get a job as president.
Right.
And I mean, you're going through the rigors now. It's also hard to get a job at Google.
Right.
We have questions, and we ask our candidates questions. And this one is from Larry Schwimmer.
Okay.
What, you guys think I'm kidding? It's right here. What is the most efficient way to sort 1,000,000 32-bit integers?
Well,
I'm sorry. Maybe
no.
we should-
No.
I
I think
that's not a.
I think the bubble sort would be the wrong way to go.
Come on, who told him this? Okay. I didn't see computer science in your background.
We've got our spies in there.
Well, why not? Let's ask a different interview question.
All right. So talking about specific numbers, though, isn't going to be all that useful. It is not a life lesson that bubble sort given 1,000,000 inputs might take as many as 500 billion steps. You can't really generalize too effectively from that and make good design decisions when writing programs. So let's focus, though, on how we might simplify this result. So I've highlighted in yellow here the result of n squared divided by 2. So 1,000,000 squared divided by 2. And then I've highlighted what the ultimate answer was once we subtracted off n divided by 2. And the claim I'm going to make now is who the heck cares if you subtract off a little old n over 2 when the first part of this formula is so much bigger. It dominates the other term. N squared divided by 2 is so much bigger clearly as n gets large, like 1,000,000, that is there really a big difference at the end of the day between 500 billion and 499,999,500,000? Not really. And so what we're going to do as computer scientists is ignore those lower order terms and take something like this and really just simplify it to the term that's going to matter the bigger our data sets get, the bigger our databases get, the more web pages we have to search, the more friends you have on Facebook. As n gets larger, we're really going to care about the largest term in any such analysis of our algorithm's performance. And I'm going to say, you know what, bubble sort is on the order of, big O, on the order of n squared. It's not exactly n squared, as we've seen, but who really cares about those smaller terms? And frankly, who really cares if we divide by 2? That's just a constant factor, and is 500 billion versus 250 billion really that big of a deal? I could just wait 1 year, let my laptop literally get twice as fast in hardware, and that sort of difference just goes away naturally over time. What we care about is the expression, the part of the expression that's going to vary as our input gets bigger and bigger. And indeed, in the real world, that's what's happening increasingly, is the inputs to our problems and algorithms are getting bigger. So big O is going to be the notation, the asymptotic notation that we just use as computer scientists to describe the performance or the running time of an algorithm, so that we can compare algorithms on different computers written by different people by using some fundamentally similar metric like the number of comparisons you're making, or maybe the number of swaps you're making. What we're not going to count is the amount of time that passes on a clock on the wall typically. What we're not going to worry about is how much memory you're using today, at least, though that's another resource we might measure. We're going to try to base our analyses on just the basic operations, the ones, frankly, that you can see most visually. So with something like big O of n squared, I claim that O of n squared is an upper bound on the so-called running time of bubble sort. In other words, if you wanted to claim that there's this upper limit on how many steps an algorithm might take, it's going to be in big O of n squared in this case, an upper bound. What if I instead change the story to be not about bubble sort, but about this upper bound? Can you think of an algorithm that we've looked at already whose upper bound, the maximum measure of time or operations, would be said to be bounded by n, a linear function, not a quadratic one that's curved? What's an algorithm that always takes no more than like n steps, or 2n steps, or 3n steps? Yeah.
Finding the biggest number in a list.
Perfect. Finding the biggest number in a list. If I'm given a list of people, for instance, each of who's holding a number, what is the maximum number of steps it should take me, a reasonably smart person, to find the largest person in that list? N, right? Because in the worst case, where might the biggest value be? Right, all the way at the end. So in the worst case, upper bound, I might have to go all the way over here and be like, here's number 8, or whatever that value is. Now, I would just be stupid if I kept going, right, looking for more and more elements if the last of them is over there. So surely n is an upper bound. I don't need to take more steps than that. So what if instead I propose that there are algorithms in this world that have a running time that's bounded by big O of log n? Log n. Where have we seen this before? Yeah. Go ahead. Like the phone book problem. What was the measure of how much time or how many tears it took me to find someone like Mike Smith in the phone book? We claimed it was log n, and even if unfamiliar or if it's a little hazy what a logarithm or exponent was, just remember that log n generally refers to the process, in this case, of dividing something in half again and again and again and again, such that it gets increasingly small as you do that. So log of n refers, sure, to the phone book example, to binary search in theory, when we had the virtual doors on the board, or when Sean was searching for something. If he had used binary search, log n would be the upper bound on how much time that takes. But those algorithms that ran in log n assumed what key detail? That the list was sorted, right? Your algorithm is wrong if your input is not sorted and yet you're using something like binary search, because you might jump right over the element without realizing it's indeed there. Now, what might this mean? Big O of 1. This doesn't mean that your algorithm takes one and only one step. It just means it takes a constant number of steps. Maybe it's 1, maybe it's 10, maybe it's 1,000, but it's independent of the size of the problem. No matter how big n is, a constant time algorithm always takes the same number of steps. So what might be an algorithm we've talked about or just intuitively that comes to you that always runs in so-called constant time? Yeah. Add two numbers. 2 plus 2 equals 4. Done. So that might work. What else? How about more real world? Yeah. Finding the first element in a list. Sure, we've actually been talking about arrays already. How do you get at the first element in an array, no matter how long the array is? In C code. You just use like the bracket 0 notation. Bam, you're there. And indeed, arrays, as an aside, support something generally known as random access memory, because you can literally jump to any one place. We can do this even more simply. We can rewind to week 0 when we did Scratch. How much time does it take for the say block in Scratch to execute? Just constant time, right? Say something. Say something. It doesn't matter how big Scratch's world is. It's always going to take the same amount of time to simply say something. So that's constant time. But what's the flip side? If that was upper bounds, what if we want to describe the lower bounds of our algorithm's running time? Almost a best case, potentially, if you will. Though these terms can apply to best cases, worst cases, average cases more generally. But let's just focus on lower bounds more generally. What's an algorithm that has a lower bound of n steps, or 2n steps, or 3n steps, some factor of n steps? That's its lower bound. Yeah. Bubble sort takes you minimally n steps. Why? Why is that? Why should that start to come to you intuitively, even if it doesn't just yet? Yeah. Exactly. In the best possible scenario of bubble sort, and a lot of algorithms, if I hand you 8 people who are already sorted, it would be foolish for you, the algorithm, to go back and forth more than once, right? Because as soon as you walk through the list once, you should realize, oh, I made no swaps, this list is sorted, exit. But that's going to take you n steps. And conversely, what's another way of thinking about it? Bubble sort is in omega, so to speak, of n, because if you look at fewer than n elements, what is the fundamental issue there? You don't know if it's sorted, right? We humans might glance at 8 people and be like, oh, it's sorted. That didn't take me n steps. But it did. Your eyes, even though you kind of have a big field of vision, you looked at 8 elements. You looked at 8 people. That's 8 steps effectively. And only if I walk through the whole list do I realize, yes, sorted. If I stop halfway thinking, all right, it's pretty sorted so far. What are the odds it's not sorted? That algorithm is not going to be correct. Might be faster, but incorrect. So now we have a way of describing a lower bound. And what about constant time? What's an algorithm that has a lower bound of its running time of 1? 1 step, 2 steps, 10 steps, but constant, independent of n, the size of the input. Yeah, and back. What's that? Printf. Okay, sure. So it takes a fixed number of steps, and I should now that we're talking about C code and not Scratch, something like say, with printf we should start to get careful, because printf does take input. It's a string, and strings do technically have length. So if we now want to pick on you, if you don't mind, technically we could argue that printf does take a variable length input, and surely it might take more time to print a string this long than this long. So what if we consider just the sorting and searching examples? What about Mike Smith in the phone book, or binary search more generally? In the best case, what might happen? I open the phone book and Bam, there's Mike Smith's number. I can call him right away. Took 1 step, maybe 2 steps, but a constant number of steps if I got lucky. And frankly, we saw on Monday your classmate get quite lucky twice in a row. And that was indeed constant time and a lower bound on the algorithm in question for finding the number 50 behind those closed doors. Now, as an aside, if you discover that both big O, the upper bound, and omega, the lower bound, are one and the same, that is the same formula in parentheses, you can also say, just to be fancy, that something is in theta of n, or theta of some other value. That just means when big O and omega are the same. Now, what about selection sort? Let's use this new vocabulary. In selection sort, what were we doing again and again and again? I was going back and forth for the list looking for whom? The smallest number. So how many steps, how many comparisons did I have to make in order to figure out who the smallest element in the list was? N minus 1, right? Because if I just start with the one I'm given and I start comparing him or her, then him or her, him or her, him or her, I can only pair elements together n minus 1 times. So selection sort similarly takes n minus 1 steps the first time. How many steps does it take me to find the second smallest element? N minus 2, because I'm being dumb if I keep looking at the same people again, if I've already selected him or her and put them in their place. And the third step, n minus 3, then n minus 4. We've seen this pattern before, and indeed, selection sort similarly has an upper bound of n squared if we do up that summation. What is its lower bound, selection sort? Minimally, how much time must selection sort take as we defined it on Monday? Propose 2 options. Maybe it's n, as before. Maybe it's n squared, as it is now as the upper bound. N squared, why? Exactly. At least as I defined selection sort, it was pretty naive. Keep going, find the smallest element. Go again, find the smallest element. Go again, find the smallest element. There's no sort of optimization in there that might let me abort after just n or so steps. So indeed, selection sort, omega of n squared. What about insertion sort, where I took who I was given, and then I plopped him or her in the right place. Then I proceeded to the second person, plopped him or her in the right place. Then the next person, plopped him or her in the right place. Notice that this is very linear, so to speak. I'm a straight line. I'm not going back and forth. I'm never looking back, really. But what's happening when I insert him or her into the beginning of the list, as we did on Monday? What's happening? Yeah. Yeah, that was the catch, right? And you might recall from your classmates, if they were making any movement with their feet, that was an operation. So if there were 3 people here and the new person belonged way over there, on a long stage like this, sure, he or she could just go to the very end. But if we're thinking about a computer and an array of memory, these people are going to have to shuffle over to make room for that person. And so that n minus 1 shufflings, n minus 2 shufflings, n minus 3 shufflings is just kind of happening behind me, not in front of me as before, in some sense. So insertion sort, big O of n squared, and for similar reasons, omega of n squared, because again, there's no clever optimization or way out to avoid that kind of cost. Now, as an aside, and as you might have seen online if you start poking around about sorts, there's so many different ones out there, some of them better than others. Indeed, bogosort is one that's kind of fun to look up. Bogosort takes a set of numbers, or say a deck of cards, randomly shuffles them, and checks if they're sorted. And if not, does it again. And if not, does it again. And if not, does it again. Incredibly stupid, and indeed, if you read like the Wikipedia article, its nickname is stupid sorts. It will eventually work, hopefully, given enough time, but that amount of time could take quite some time. So if I could, let's speed things up from Mary Beth's example earlier by having a few more elements, but 2 more processors. 2 people, if you wouldn't mind joining me. How about one over here? And let's go. No one over there. No one over there. Okay, you with the black shirt? Yes, come on down. All right, what's your name? What's that? Peter. Peter. David, nice to meet you. All right, we have Peter here. If you want to come on to the table over here. And what's your name?
Alina.
Alina. Okay, nice to meet you. Alina, meet Peter. Peter, Alina. And we'll need Andrew up here as well, please. And your challenge is going to be to sort a deck of cards. And if unfamiliar, deck of cards should ultimately be sorted a little something like this, where we'll do the clubs, then the spades, then the hearts, then the diamonds, from ace as a 1 all the way up to king. The cards I'm going to give you are going to be 52 in quantity. We're going to similarly time you in just a moment. We're going to throw Andrew up on the screen here so as to watch as you do this. And so that all of this is all the more visible, these are the cards I got on Amazon. So they are already randomly sorted. And we're going to time you, and we're going to keep it real this time. So we're going to try to pressure you, because otherwise this will get tedious quickly. If you could proceed to sort 52 elements together via some means now. And again, as we watch these guys do, what in the end is going to produce an obvious result, think about really how they're each doing it, how you might describe it. Because again, these are all processes, algorithms that we take for granted as a human, but you've probably long had intuition, long before you even thought about, it's okay, long before you even thought about taking a computer science class, you might have had the intuition with which to solve problems like this, but once you recognize the patterns and begin to formalize the steps with which you're solving these problems, you'll find that you can solve much more interesting and much more complex problems quickly. So someone from the audience, what is at least one element of the algorithm that they're using here? What's that? Oh. By suit. So first they are clustering all of the diamonds together, it seems, all of the hearts together, it seems, and so forth, without respect for the numbers on the cards. And now they appear, for instance, to be sorting them by number. Very good. All right. So what's going to be the final step then here? Once we have 4 sorted suits, what do we need to do to the 4 piles in order to achieve one sorted deck, quite simply? So we need to merge them again. And so there's an interesting idea that, again, dare say is very intuitive, even if you might never have slapped that kind of label on it. This fundamental notion of dividing the problem, not in half this time, but at least into 4 pieces, solving pretty much fundamentally identical problems in isolation of each other, and then merging the results. And excellent. Done. All right, a big round of applause if we could. I have no idea what you'll do with these, but here you go. Thank you so much. So let's see, 2 minutes and 8 seconds, if you'd like to challenge your friends. What then is going to be a takeaway from this that we can leverage more generally? Well, think back to this array of numbers, and think back now to some of the pseudocode we've written in the past. And this was the pseudocode for solving the phone book problem, whereby in pseudocode I enumerated a more methodical way of describing how I did the very intuitive human algorithm of dividing the phone book in half, repeat, 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 until I find someone like Mike Smith, if he is indeed in the phone book. But I kind of used what I'll call a very iterative approach here. In particular, notice line 8 and line 11. Those are evidence of an iterative approach, a looping approach, because that's exactly the behavior they induce. Those lines both say, go to line 3. And you can kind of think of that in your mind's eye as being a loop. It's telling you to go back up to step 3 and repeat again and again and again. But what if we leverage a key idea here that we didn't the last time and simplify line 8 and line 11 and their neighbors as just this in yellow? It's not fundamentally shortening the pseudocode very much, but it's fundamentally changing the nature of my algorithm. What I'm now saying in step 7 and step 10 is search for Mike in the exact same way, but just in the left half or the right half. So in other words, if I start from step 1, pick up phone book, open to middle of phone book, look at names. If Smith is among names, call Mike. Else, if Smith is earlier in book, step 7, search for Mike in left half of book. But that kind of feels like it's leaving me hanging, right? In yellow is an instruction, but how do I search for Mike in the left half of the phone book? Where do I have an algorithm with which I can search for someone like Mike Smith? Well, it's staring us in the face. I can literally use the exact same program, effectively going up to the top again and rerunning the same lines of code. So even though this should feel like a bit of a cyclical definition, where you're answering someone's question by just sort of asking the same question again, like why? The reality is, because we've hard-coded a couple of special lines, step 4, which is an if, and step 12, which is effectively another branch, because we have those stopgap measures, this algorithm will terminate if we find Mike or if we don't. But in step 7 and 10 now, we have what we'll call a recursive algorithm. And recursion is indeed a powerful idea that's a little mind-bending at first that we can now apply as follows. Merge sort will be the last sort that we look at least in class formally, and it's fundamentally different from those last 3, and certainly last 4 if we include bogosort. Here's the pseudocode for merge sort. When on input of n elements, so given an array of size n, if n is less than 2, return. So why do I have that sanity check first? What's the implication if I hand you an array whose length, n, is less than 2? Right, it's already sorted, obviously, right? Because the list either has 1 element, which is trivially sorted because it's the only thing there, or it's of size 0, which means there's nothing to sort, so by nature it is sorted. There's just nothing wrong there. So that's our so-called base case. That is similar in spirit to what we did with Mike. If Mike's in the phone book column, if he's not there, give up. It's a so-called base case to make sure this algorithm at the end of the day will stop in certain circumstances. But here's the leap of faith now. Else sort the left half of the elements, then sort the right half of the elements, and then merge the sorted halves. And here's where it feels like we're copping out. I've asked you to sort an element, and I'm saying, okay, do it by sorting the left and sorting the right. But I am saying one other thing, and this is the key theme, it seems, in the intuition thus far. There's this third step of merging, which even though it seems so dumb in spirit, like just merge things together, it seems to be a key step toward the reassembly of 2 problems that were divided ultimately in half. So merge sort, let's do this. If you'll humor me with one more demonstration, just so that we have some numbers to work with. Can I exchange 8 stress balls for 8 people? All right. How about you 4 in this section? 5, 6, and let's do 7, 8. Come on up. Okay, let's do, yeah, okay. Minus 8, there we go, plus 1. Excellent. All right, come on up. Let's quickly give you numbers. Number 2, number 3, number 4, number 5, 6, 7, and 8. I did 8 correctly this time. Okay, so go ahead if you could, and let's sort in the original order that we had yesterday, which looked like this, if you wouldn't mind. And let's do it in front of the table. All right, so merge sort. This is where it's going to get kind of interesting because I seem to be giving myself so much less information today. So merge sort, first of all, on input of n elements, n is obviously not less than 2, it's 8, so I have some more work to do. So now mentally we as a class are now in the else branch, which means 3 steps. First, I have to sort the left half of the elements. So how do I go about doing this? Well, I'm going to kind of mentally divide the list here. You don't have to physically move, and I'm going to focus only on the left half of the elements here. So how do I go about sorting a list now of size 4? What's my algorithm? First, I check, is n less than 2? No. So I proceed to the else block again, sort left half of elements. So now, again, mentally, and this is where you kind of have to accrue a lot of mental history, if you will. Now I'm sorting the left half of the left half. All right, so now I call my same merge sorting algorithm, is n less than 2? No, it is 2, so I have to sort the left half and the right half. So here we go, sort the left half. Okay, why don't you take 1 step forward? What's your name?
Darren.
Dan. Dan has stepped forward?
Darren.
Done. Did you say Darren or Dan?
Darren.
Darren, okay. Darren has stepped forward, and he is now sorted. And this is almost an inane claim, right? I don't really seem to be achieving anything, but let's proceed. Now let me sort the right half of the elements. What's your name? Luke. Come on, step forward. Done. I have sorted Luke. The left half is now sorted, and the right half is now sorted. But again, there's a key step here. What do I next need to do? Merge the sorted halves. Now we're going to just have everyone back and forth in this way because I kind of need some scratch space. It's almost like these guys are on a table and I need some room to move them around on. So I'm going to merge you guys by looking at the left half and the right half, and who obviously comes first, left half or right half? So right half, so let's move Luke over here to Darren's original position, and now to merge the left half in, Darren's going to move right there. So it feels like almost a bubble sort effect, but my fundamental algorithm, very different this time. But now's where things get a little annoying because you have to rewind mentally. Where did I leave off? I've just merged the sorted halves, which means I'm where in my algorithm? I have to sort the right half, right? If you rewind, literally on the video, you'll see that we got to this point of Luke and Darren by sorting the left half of the left half. Then we merge those sorted halves, which means the next step is sort the right half of the left half. All right, so let's do this more quickly. All right, 6, I'm going to claim you are now sorted. Come on forward. What's your name?
Adriano.
Adriano. Adriano is now sorted. And what's your name?
Alex.
Alex is now sorted. So left half, right half, what's the final step? Merge. Pretty trivial, so I'm going to merge in 6, just take a step back, 8, take a step back, and now notice this is a useful takeaway. What is now true about the left half of the list, irrespective of how we began? It is sorted. Now, it's not sorted in the big scheme of things, but it is sorted independently of the other half. Now, what step am I on if I keep rewinding how the story began? Now I have to sort the right half. So now we're way back at the beginning of the story, and let's do this more rapidly. So I'm going to sort the right half of the whole list. What's the next step? Sort the left half of the right half. Sort the left half of the left half of the right half. And what's your name?
Omar.
Omar, take a step forward. Done. Left half is sorted. And what's your name?
Chris.
Chris, take a step forward. You are now sorted. What's the key step now? Merge. So 1 is going to merge into place here, if you could take a step back. And 3 is going to take a step back, merge. So the left half of the right half is now sorted. Frankly, this algorithm feels like we are wasting way more time than before, but if we did this in real time, we'll see what the takeaway is going to be. Now here I am, right half of the right half. Let me go ahead and sort the left half. Step forward. What's your name?
Ramsey.
Ramsey is now sorted, and what's your name?
Marina.
Marina is now sorted as well. If you take 1 step forward, key step here is now merge. I'm going to pluck from my 2 lists, left and right. 5 is going to come first, and 7 is going to come next. And again, this is deliberate. The fact that they're taking steps forward and back is meant to represent that we can't do this algorithm in place as easily as bubble sort and selection sort and insertion sort, where we just kept swapping people. I literally need a sort of scratch paper in which to put these folks while I do the merging, and then I can put them back in place. And that's key because I'm using a new resource, space, not just time. Okay, this is amazing. Left half is sorted. Right half is sorted. Now that key merging step. How am I going to merge this? So if you'll follow sort of my left hand and right hand, I'm going to point my left hand at the left half, my right hand at the right half, and now I have to decide step by step whom to merge in. Who obviously comes first? Number 1. So come on over here. Here's our scratch pad. So now number 1, and notice what I'll do with my right hand. I'm going to move my right hand 1 step over to point at number 3, and now I have to make the same decision. And actually stand right in front of Luke here, if you could, because this is our scratch pad. So who comes next? We have Luke with number 2, or Chris with number 3. Obviously, Luke with number 2, so you come here. But my left hand now is going to be incremented to point at Darren. And here's the key takeaway with merging. I'm going to keep doing this, obviously, if you kind of follow the logic. But my hands are never going to go backwards, which means I'm only ever moving to the left with my merging process. And that's going to be key to our analysis in just a moment. So now let's finish this up rapidly. So 3 comes next. Then 4 comes next. And now 5 comes next. Then 6. Then 7, and then finally 8. Feels like the slowest algorithm yet, but not if we actually run it at the same sort of clock speed, so to speak, with the same ticking clock as before. Why? Well, let's take a look at the end result. Let's go back over here. Let me pull up a demonstration visually of what we just did. Zooming in here on this page here. Telling Firefox that we want to queue up in this box, let's say bubble sort, with which we're now well familiar, selection sort, which is another fairly straightforward one, and now today's merge sort, which will be our climactic ending. The reason it took so much longer here with humans and me verbally is obviously I'm explaining every step. But if you simply execute this, much like we did bubble sort and selection sort, not only visually, watch just how much more efficiently this leveraging of division and conquering can be when applied to a data set that's not even size 8, but even much, much bigger. I give you merge sort side by side with these other algorithms. This is going to get painful quickly, and the ending is not particularly climactic. They just end up sorted. But the key takeaway is that look how much faster merge sort was. Unless you think I'm just kind of messing with you, if we do this one final time, let's reload this. Let's go back and choose bubble sort. And just for kicks, let's choose insertion sort, just for good measure. And this time again, let's choose merge sort. And let's actually run these side by side. And it's not, in fact, a fluke. What I've effectively done is I've divided my input in half again and again and again, and there's only so many times you can divide your input into halves, left and right. What's the formula that we keep seeing that describes the division in half again and again and again and again? Log n. But then there's one other key step. This algorithm is not log n steps. If it were only log n steps, we would be in the same problem as before where we can't be sure everything's sorted. You have to minimally look at n elements to be sure n elements are sorted. Otherwise, it's a leap of faith. So it's minimally log n steps. But what about this key merging step where I merged my left half and right half and walked across the stage? How many steps is that to merge? It's n. But I didn't just merge the final time. On each of those nested calls, on each of those nested merges, I still I merged these two guys, then these two guys, then these two guys, and so forth. So I did merging again and again. How many times? Well, every time I divided the list in half, I did a merge. Divide the list in half, do a merge. So if dividing the list can be done log n times, and the merging ultimately takes n steps, what might be now the upper bound on the running time of our algorithm? N log n. And indeed, that's what we've achieved here. So the feel that you see visually when those three things run side by side is n squared against n squared against n log n, which fundamentally we'll see not only today but in the future is much, much faster. A round of applause for these guys. I will reward them with stress balls. Let's adjourn here today, and we will see you on Monday.
Have a new message. iPhone Metro No Remix. Incoming call from Metro. No. Drop it.